All right, so I guess first of all, your exams you took last week, I'll have those graded for you by Thursday. You can view those. We'll set aside some time at the end of class. All right. As I said this week, we're going to be focusing on these experimental techniques. There's three that we're going to sort of lay out, introduce first here in lecture. We'll also be using them throughout the semester in lab. They're very important techniques in organic chemistry. The first one we're going to talk about is infrared spectroscopy, or more simply referred to as IR spectroscopy. I will say right off the bat that I first learned about this nerding out in the library when I was an undergrad. And because of that, I really thought that that was infrared spectroscopy. And I said it wrong to myself about 1,000,000 times. And it's stuck in my head wrong. So I'm trying to get better at it. It is infrared. But you'll probably hear me slip up and say infrared a few times. All right. First, we're actually going to focus on the second word here, though, spectroscopy, because there are a lot of different spectroscopy techniques that we use in chemistry, and they all have the same basic format. All right, so what all spectroscopies are doing is they take advantage of the interactions between atoms and photons. What do I mean by photons? Yeah, the particles that light is made out of, all right? Which, first of all, just to take a step back and kind of be a nerd, it's already pretty cool that we're taking advantage of these interactions. The universe is filled with many, many different particles. There are muons and neutrinos that are raining down on us from space, and we just have no idea. They're passing through us right now, and we would never know because what we're made of, protons, neutrons, and electrons, they don't interact with those particles, right? So, millions of particles out there. Most of them don't interact with us because of what we're made out of, but photons do. So it turns out that photons do interact with protons, neutrons, and electrons, the thing that we're made of. So all spectroscopies have the same basic setup where there's some photon source. So for example, a simple light bulb. And that photon source is sending in photons into your sample. All right, so here's my sample. My photon source is sending in those photons, but what happens is some of those photons get absorbed by my sample. So not everything that we send in comes back out the other side, and then we have some sort of a detector that's going to measure what comes out. All right, so our sample absorbs those photons. All right, and if we used like a simple light bulb like what we have in our overhead lights as our photon source, that would be an example of visible spectroscopy, using photons that are in a certain range of our electromagnetic spectrum. All right, so the electromagnetic spectrum, these are all the possible different frequencies that we can have of light, of photons. All right, our eyeballs are photon detectors, but they can only detect photons in this very narrow range of this spectrum here, from between 400 nanometers to 700 nanometers wavelength. And I guess I want to say the fancy little V here, this represents the frequency of light, or our lambda here represents wavelength. These are one and the same pieces of information. If you know one, you can always figure out the other. Certain spectroscopies like UV-Vis like to talk in terms of wavelength. Other spectroscopies, like we're going to see IR, likes to talk in terms of frequency, but they're kind of just one and the same. All right. Again, our eyeballs are photon detectors. They can detect light in this narrow range of 400 to 700 nanometers. But photons can have longer wavelengths or shorter wavelengths. All right. And those will interact a little bit differently. So again, what you would have talked about in Chem 1B would have been using light in this UV vis region. And now what we're going to be talking about is using light in this infrared region. So longer wavelength photons that our eyeballs cannot detect. All right, so IR spectroscopy. It uses photons in the infrared portion of the electromagnetic spectrum. All right, so our photon source is going to be using photons that emit light in that infrared portion of that electromagnetic spectrum. All right, those photons, again, they get absorbed by our sample. When we were talking about UV vis spectroscopy, our electrons were getting excited, and that's why those photons were being absorbed. When we use photons from a different portion of our spectrum, they're not interacting with the electrons in our molecules anymore. They're actually interacting with the bonds in our molecules. All right, so our molecule has these covalent bonds. Bonds are always moving about, right? So we have these two atoms bonded to one another, and they're kind of vibrating back and forth about that bond. Well, if we send in a photon in the infrared portion of our electromagnetic spectrum and that photon gets absorbed, what it's doing is causing those bonds to vibrate even more, right? So they're vibrating back and forth. All of a sudden, they absorb a photon, and now they're vibrating even more, right? That's where the energy of that photon goes into vibrating bonds, our covalent bonds. All right, so IR spectroscopy. Photons are absorbed to excite our bond vibrations. So what that means is that different chemical bonds will absorb in different portions of our IR spectrum. All right, so because of that, this is why this is such a useful technique in organic chemistry. Our IR spectroscopy allows us to see different chemical bonds. Okay, and why is that so super useful in organic chemistry? Well, because as you saw in your weekend activity, the world of organic chemistry, we take all these molecules and we divide them up based on the functional groups that are present in those molecules. A lot of how we understand an organic molecule is based on what functional group is present. All alcohols tend to have similar properties. All alkanes have similar properties, et cetera, et cetera. So what IR is allowing us to do is to determine our functional group. All right, that is the power of IR spectroscopy. We can determine the functional group that is present in our molecules. All right, so that's the pro of IR. We get to see our functional groups in our molecules. All right, the con is that's kind of all we can see. So we don't have any size or shape information from our IR spectrum? Yes, we can see if there is that OH bond in an alcohol in our molecule, but all alcohols are going to look basically the same in an IR spectrum. All right, so although we can tell information about our functional group, that's kind of where it ends. We're kind of limited there. All right, so doesn't matter whether we have 2 carbons or 8 carbons, they're both going to look the same in terms of our IR spectrum. All right, so then why do we bother to use it? All right, the pros, well, first of all, functional group is a good amount of information. All right, but there's 2 other like practical pros for IR spectroscopy. One is that it's easy to use, and the other is that it's relatively cheap. All right, so again, we'll be using these instruments in the lab, but what you'll see is they're incredibly easy to use. You walk up, you put your sample on this little place in the instrument, and you press go. Done. You get your IR spectrum. Right? So incredibly easy to use, very straightforward, as well as in the grand scheme of things, the instrumentation is really cheap. So our IR spectra that we have in the back, instruments that we have in the back, brand new, probably like $12,000, which like, I'm not gonna go get one for my bedroom or something like that, right? But in the grand scheme of chemistry equipment, that is incredibly cheap. The NMR sitting right next to it is upward of $150,000, right? So more than 10 times more expensive for that one instrument than the other. So in the grand scheme of things, an IR is something that's fairly cheap to put in your lab, as well as very easy to use, right? So those are the pros. We get functional group information. For this other stuff, our size and our shape of our molecule, we're gonna have to use our different experimental techniques that we'll cover later. All right, this one right here again allows us to determine functional group. That's what you want to have synonymous in your mind with IR spectroscopy, is that we can determine functional groups. That's the name of the game. All right, cool. So first of all, let me show you what an IR spectrum looks like. We go to the back, we take our sample, we put it on this instrument and press go, and it spits out this graph. All right, and this graph right here is what we're going to analyze to get our functional group information. All right, so let's pick apart this graph real quick. Okay, first of all, on our x-axis, we have wave number, which is a fancy way of saying frequency of our photons. So each point along the x-axis here represents a different photon that we're sending into our sample, right? So down here, this is the photon that has a frequency of 1,000 inverse centimeters. This photon has 2,000 inverse centimeters, 3,000, et cetera, and everything in between. So these are all the different photons that we're sending into our sample, and we're measuring whether or not they get absorbed or whether they just pass right through our sample. All right. One of the things that's weird about IR compared to all of our other spectroscopies is our graph is kind of upside down. We have these downward facing peaks here. All right, most of the time when we look at these graphs, our peaks are facing upwards, and that means that our photons are getting absorbed. For whatever reason, historical reasons, instead of absorbance in IR, we look at percent transmittance, which is just the inverse of absorbance. So percent transmittance is how many photons make their way through the sample rather than how many photons are being absorbed by the sample, but those are one and the same pieces of information. All right, so that means that a point that's up here at the very top of our graph, this is our photon is not absorbed. If we have one of the peaks at our bottom of our spectrum here, that means our photon is absorbed. All right, so again, we have these downward facing peaks in our IR spectrum. Okay? Cool. So how the heck are we supposed to get functional group information from these squiggly lines here? I know everybody's like, oh no, totally, I know what functional group's in this molecule. No, we gotta learn how to read these IR spectra, right? So how do we get that information from these little lines about our functional group? So first of all, where on the x-axis we see our peaks gives us a lot of information, all right? We can cut this IR spectrum up into these different regions. It turns out that if we look all the way here at our lower frequency photons, down here is where all of our single bonds will be absorbing, right? So remember, it's the bonds that are absorbing these photons. Single bonds will absorb at these lower frequency photons. If we start moving up in frequency, next we get to our double bond region. So any peaks that we would see in this region here would correspond to double bonds. We move a little bit further up on our spectrum. Everything we see in this range here would correspond to triple bonds. And then lastly, our highest frequency photons, these correspond to single bonds, but specifically something bound to hydrogen. It turns out that hydrogen, just being so teeny tiny small, absorbs in a different portion of our spectrum than our other single bonds do. Okay, so based on where on our x-axis we see peaks, we can get information about the functional groups in our molecules. All right, so let's talk about how we analyze an IR spectrum. Let's say I go to the machine, it spits me out a graph that looks like this. How am I going to analyze this spectrum here? All right, step one is we're going to cut it up into those different bonding regions that we talked about. All right, so when I get my little graph here, I'm going to separate it out based on my single bonds, double bonds, triple bonds, and my something with hydrogen region. All right, now we can look, and I'm going to be a little bit lazy in the numbers that I pick here because I like nice round numbers that I can remember a little bit easier. So when we cut this up, we're going to cut it up at 1,500, 2,000, and 2,500. Nice round numbers that we can remember. All right, meaning that I'm going to lay down a marker here at 1,500. Boom. I'm going to lay down a marker here at 2,000. Boom. And I'm going to lay down a marker here at 2,500. This is now my 4 regions of my IR spectra that I've separated out. And I'm going to look for peaks in each one of those regions. All right. This first one here, all the way at our lower frequencies, these were our single bonds. Our next region up were our double bonds, then our triple bonds, and then lastly our something with H portion of our spectrum. Right, so again, first thing we did was we cut up this spectrum, we broke it up into these different regions, and we're going to look for peaks in each one of these regions. All right, this single bond region here has a special name here. We call this the fingerprint region. All right, because much like your fingerprints, each molecule has a unique pattern in that fingerprint region. All right, but also much like your fingerprints, just by looking at one doesn't really help you figure out what person you're talking about, right? Maybe for the police who are going to run it against some database of other fingerprints that they have, they can help identify people. But us ourselves just looking at it, not much information there. All right, and much the same with the fingerprint region of our IR spectrum. It's great if we're going to search this graph against a database of other graphs. But for our purposes, at least for the most part, and especially to start out here, we're straight up going to ignore that fingerprint region. It's just way too complicated. There's way too much going on. There will be specific things that we'll learn to look for in this region, but for the most part, we just ignore it. Every bit of information we get about our functional groups will come from the other part of our spectra here. Information in this fingerprint region is just buried under too many peaks. All right, so we cut it up into these different regions, and then we ignore the fingerprint region, and we're going to analyze our peaks in the other portions of our spectra. All right, so when we analyze a peak here, what do I mean by that? So let's look here. We got this same graph. I'll lay down my same 1500, 2000, 2500, and then I'm going to ignore that fingerprint region. All right, so then we're going to look at peaks here, and we're going to analyze those peaks. So I'm going to take, for example, this big peak right here to analyze. All right, we would do that for all of our peaks that we see in our structure here, but let's take this one as an example. When we analyze our spectra, we always give these same three pieces of information. The wave number of that peak, aka where on the x-axis we're absorbing. The intensity of that peak, aka where on the y-axis. And lastly, the shape of that peak. All right, I'll explain what this means here in a second. But let's go through. If we're going to analyze this peak right here, I'm again going to give the wave number of that peak. For really sharp peaks, you can just like report that maximum value. For these broader peaks, it's better to report some sort of a range here, right? So I'm going to look and say, all right, my peak is from 32 to 3,600 inverse centimeters. Okay, that's my peak here that I'm analyzing. There to there about. All right, so step one, that wave number of your peak. Step two, the intensity of the peak, so just how much it's being absorbed. And they don't really put a numerical value on that. I could say, oh, look, my percent transmittance is 10% here. But really, they throw it into one of three buckets in terms of intensity. Your intensity is either weak, moderate, or strong. Okay, and to be clear, by strong, we would mean a peak that extends all the way down on our graph. Moderate would be about midway, and weak would be something that was closer to baseline there. All right, so by intensity of the peak, we mean just how much of a downward facing, just how many photons are being absorbed. So this peak here coming very close to my 0% transmittance, we would call this a nice strong peak. All right, and then the shape of our peak, really kind of the breadth of that peak, again, they throw into one of three buckets. It could be narrow, it could be medium, or it could be broad. All right, and so just to be clear here, narrow peak would mean that nice sharp peak, just one sharp spike in our graph. A broad signal would be if that peak is extended out a little bit wider. So in this case here, this would be a nice broad peak in my spectrum. All right, so for all of our peaks in our IR spectra, ignoring that fingerprint region, we characterize or analyze those peaks according to these three factors here. All right, our wave number, our intensity, and our shape. All right. We'll talk about why, we'll talk about this, each functional group in particular. It turns out that this functional group corresponds to an alcohol here. And in fact, that's what this big broad peak over here represents. It's in our something with hydrogen region, right? And in particular, this is a characteristic OH peak. Okay? But like we said, We don't get any size or shape information from our IR spectra here. So if I took the IR of a completely different alcohol, I would see that same peak, and otherwise my graphs look pretty much the same. There is some difference down here in the fingerprint region, but again, that's really hard to interpret. So again, all our IR is telling us is what functional groups are present in our molecules. All right, we'll need to do more techniques, more experiment to figure out stuff like size and shape information. Cool. All right, now we're going to go kind of one by one for what we expect to see for these different bonds. And we're going to start first with our carbon-hydrogen bonds, because those are present in all of our organic molecules. All right, so first of all, where on our spectrum are we going to be looking for carbon-hydrogen bonds? In the something to hydrogen region, right? So this region up here is going to be where our something with hydrogen bonds are, or rather where our carbon with hydrogens are. It turns out that depending on the hybridization of that carbon, they'll absorb at slightly different wavelengths, slightly different frequencies. Okay, so our sp3 hybridized carbons and their hydrogens will absorb around 2900. If we only have carbons and hydrogens, all single bonds, what functional group is that? Somebody bust out your functional group activity. All single bonds. What one is that? Those are alkanes. If we have an sp2 hybridized carbon, so we have a carbon-carbon double bond in there, we absorb slightly higher than 3,000, around 3,100. If we have carbon-carbon double bonds, what functional group is that? Alkenes. And then lastly, if we have an sp hybridized carbon with a hydrogen on there, right? So a carbon-carbon triple bond, that absorbs even higher up, around 3,300. Carbon-carbon triple bonds would be what functional group? Alkynes. All right, so these three different hydrocarbons that we can distinguish which one we have based on those carbon-hydrogen bonds and where they absorb on our spectrum. All right, so first of all, let's take a look at these sp3 hybridized carbons and hydrogens. Importantly, just about every molecule contains sp3 hybridized carbons, right? Even if there is a carbon-carbon double bond in there, most likely if it's a larger molecule, it's going to have some sp3 hybridized carbons. So this cluster of peaks is what we'll see in just about every IR spectrum that we look at. All right, and since there's many carbons with hydrogens, we see a bunch of peaks kind of all stacked on top of each other. All right, so this little cluster here is our sp3 carbons and hydrogens. If we go back to our spectrum that we were looking at with our alcohol, we can note we had that same cluster of peaks in that spectrum as well. All right, again, this will be common in just about every organic molecule because they just about all have some sp3 hybridized carbons. All right, so our sp3 hybridized carbons, again, we got those same three characteristics. Our wave number here, all right, in this case, around 28 to 3,000, 2,800 to 3,000 inverse centimeters. We get a bunch of medium strong peaks, a bunch of narrow peaks kind of all clustered together, right? So this is an overlay of many sharp peaks kind of stacked on top of one another. Cool. All right, and so this is kind of zoomed in on that something with hydrogen region. And what we see is that they've got this extra marker that they lay down at 3,000. So we said that when we lay down our markers, when we cut up our spectrum, we're going to cut it up into these three groups here. All right, our fingerprint region, double bond region, triple bond region, and then something with hydrogen. There's one more marker that's helpful to lay down, and that's to help us distinguish between alkanes, alkenes, and alkynes. This will sort of not cut up a different region. It's just a helpful marker to lay down, and that's right at 3,000. All right, that's because all of our sp3 hybridized carbons and hydrogens are always just south of 3,000. All right, if we have an alkene or an alkyne, we'll see a peak slightly above that extra line that we just laid down at 3,000. All right, so a carbon-carbon double bond, an sp2 hybridized carbon and its hydrogen. Right, this one's sp2 hybridized. Now we have this extra peak sitting just above that 3,000 marker. All right, so by laying down that extra marker at 3,000, we can see if we have an alkene, because we'd have something sitting just above that marker, right? Around 30, 50, medium to strong. I don't know, I kind of disagree with that. They can be fairly weak. So we're going to say weak to strong. All right, but always nice and narrow. And again, always north of that 3,000 marker that we laid down. And if we have an alkyne, we again see a peak north of that 3,000, but now we're way far north of that 3,000 marker, around 3,300. Again, a nice medium to strong peak that is always nice and sharp, right? Narrow. Okay, so all of these examples here contain those sp3 hybridized carbons and their hydrogens. But if we have an alkene, we have another one just north of that 3,000 marker. And if we have an alkyne, it's even further, around 3,300, indicating that carbon with its hydrogen, sp hybridized carbon with its hydrogen. Okay. Now, importantly, we're looking at carbon-hydrogen bonds. So not all alkynes, for example, will have those. It's got to have a hydrogen right here, right? If there are carbons on either end, then we wouldn't see that peak in that region. All right. Same with our carbon-carbon double bonds. If they're all carbons on about that double bond, we wouldn't see that absorbing in that region. Instead, we'd have to look at a different portion of our spectrum. We could still see our carbon-carbon double bond or our carbon-carbon triple bond, right? So double bonds and triple bonds will also show up in our spectrum here at a slightly different place. So as we said, and we used nice round numbers, we said from 1,500 to 2,000 was our double bond region, and from 2,000 to 2,500 was our triple bond region. All right, carbon-carbon double bonds tend to be at the lower end of that double bond region, sort of medium in size and nice and sharp, nice and narrow peaks. Another kind of notable one, and we'll see this guy quite a lot in organic chemistry, but especially in the second semester, this six-membered ring where every other double bond, every other bond is a double bond. This is what's called a benzene ring. It's a pretty famous molecule in organic chemistry. Again, we'll spend just about half of next semester talking about benzene and benzene derivatives. All right. Importantly, they also are kind of at the lower end of that region, and they tend to be a lot weaker than other carbon-carbon double bonds. But you see a few of them in a row, a few narrow peaks that are on the weaker end, and we'll see some example of some benzene rings as we go throughout the week. All right, so we're going to take a look at this spectrum here, and this is actually two spectra that are laid on top of one another here. In red, we have an alkane, and in blue, we have an alkene. So carbon-carbon double bond. All right, and so let's take this spectrum and cut it up here at our 1,500, 2,000, 2,500, And then we said we got that extra marker that we're going to lay down. What's that one at? 3,000. All right, so all the way over here, what did we call this portion of our spectrum? The fingerprint region. And what do we do with the fingerprint region? We ignore it. All right, again, as we kind of get more advanced, we'll look for some specific things in that region, but for the most part, we're just going to ignore it. That next region up is what? Then we get double bonds, then triple bonds, then our something with hydrogen region. All right, so there's two features here that we can see that are distinct in our alkene spectrum compared with our alkane spectrum. The first one is in that double bond region. All right, so here is my carbon-carbon double bond here. They both have a bunch of sp3 hybridized carbons and hydrogens, so they both have that cluster of peaks that are south of that 3,000 marker, right? This is my sp3 carbon and hydrogen. But I got this extra little blip on my blue spectrum here, this peak over here, just north of that 3,000 mark. What does that correspond to? So my carbon-carbon double bond is absorbing over here. This is in my something with hydrogen portion of my spectrum. So what must this peak correspond to? The carbon-hydrogen bond, but specifically that sp2 hybridized carbon-hydrogen. All right, so we can see we got these two extra peaks compared to my alkane spectrum. First one corresponding to the actual carbon-carbon double bond, the other one corresponding to the hydrogens that are bound to those sp2 hybridized carbons. If we want to see an example of a triple bond, here is hexine. All right, again, kind of laying down our markers. All right, again, we're going to go ahead and ignore that fingerprint region. We don't see anything in the double bond portion of our spectrum, but now in our triple bond portion of our spectrum, we see that carbon-carbon triple bond. We again have this same cluster of peaks. We always see this corresponds to what? Carbon-hydrogen, but specifically those sp3 hybridized carbons with hydrogens. And then I got this extra peak over here in my something with hydrogen region. What does this correspond to? Right, so an sp carbon with its hydrogen. All right, right around that 3,300 mark. Cool. All right, so alkanes, alkenes, and alkynes, there's kind of two different things that we can look for here. One are the different signals that we see from our carbons with their hydrogens bound. And then the other is by looking in either the double bond or triple bond region of our spectrum. All right, both of these will help us conclude what our molecule's functional group is. Moving on, we're going to go to alcohols next. By alcohols, I'm talking about what functional group? Those OHs. And those are going to absorb where in our spectrum? Something with hydrogen up here in this region. All right, these are one of the easiest peaks to see because they are characteristically very broad peaks. All right, so if I just kind of cut up this spectrum, Laying down my extra marker around 3000. I again see this cluster of peaks I'm always going to see corresponding to my sp3 carbons with hydrogens. But then I also get this very broad peak here. This is the one that corresponds to that OH bond. All right, so our alcohols tend to have a range of between 32 and 3600. Nice and strong peaks, very obvious peaks on our spectrum, but they have this characteristic broadness to them that makes them very easy to spy. All right, one other thing that I want to point out on this spectrum here is this guy over here in my double bond region. There are not any double bonds in this molecule, right? My molecule here is ethanol, just simple 2 carbons, 1 OH group. All right, this is when IR gets to be a little bit more art than science here. We're laying down these markers, cutting this up into these different regions. Well, that's not scripture, all right? There's nothing that says that there's only going to be double bonds in that double bond region. Every once in a while, you see these little blips, and you don't know whether or not there's something that you're going to be, supposed to be focused on, all right? Importantly, you're never really doing IR in a vacuum, right? You always usually have some piece of information about what you're expecting to see. You're doing a chemical reaction. You know what your reactants are that you're starting with, right? So you're never kind of just showing up completely blind trying to analyze a spectrum. You're going to kind of piggyback off what it is that you know and what your expectations are when you go in to read this, all right? It turns out that this thing here is not an important peak in our IR spectrum. All right, so again, sometimes a little bit more art than science. There's some judgment calls that have to be made that just come with experience. All right, another really obvious peak in our IRs are our carbonyl bonds. What do I mean by carbonyl? Carbon-oxygen double bond. All right, and these are going to show up in which portion of our spectrum? The double bond region. All right. So if we cut this up here, lay down our marker at 15, 2000, 25. Put down that extra one at 3000. We get this very pronounced, very sharp peak in our double bond portion of our spectrum. This is what corresponds to that carbonyl group. All right, so our carbonyl bond around 17, we're going to say 1700 inverse centimeters, always very strong and very narrow. All right, so that nice sharp peak in your double bond region is indicative of a carbonyl group. Okay, and we can look, we kind of compared these in a previous slide, but maybe we'll make a little bit more sense looking at it. All right, if we have a carbon-carbon double bond versus a carbonyl bond, we can see just how much stronger that carbonyl bond is than our other double bonds. All right, so that nice, sharp, very strong, very narrow peak corresponds to that carbon-oxygen double bond. The exact position of that peak does give you a little bit of information about your environment of your carbonyl bond. This is kind of getting into the weeds here, but just sort of helpful to note. So a normal old ketone will reliably absorb around 1720. If there's a double bond next door, all of a sudden it's a slightly lower wave number that we're absorbing at. Right? So we can kind of distinguish between these two molecules based on exactly where that carbonyl signal is. Likewise, an ester absorbs at a slightly different wavelength than a ketones carbonyl. And since these are nice, sharp, reliable peaks, having these numbers can help. I'm going to say you don't have to memorize these numbers, all right? We're going to have like a cheat sheet that we're going to have available to us that has these things listed, but it's just kind of notable to keep in mind. That carbonyl peak, it's so sharp and so strong that the exact location can also give you some important information about your molecule. All right, a carboxylic acid, what am I talking about there? So C double bonded to an O, and what else? Now we have an OH. All right, so we have two different bonding patterns that we've already discussed here. We have our carbonyl bonds, right? Our carboxylic acids are a carbonyl-containing functional group, so we should see a peak corresponding to that carbonyl group. But they also have that hydroxyl group, so we should see that OH bond as well. All right, so kind of a mashup of the two functional groups that we discussed previously. Okay, so first of all, looking at this here, I'm going to cut it up. All right, first I just want to note we do have our nice, sharp carbonyl peak here, right around that 1700 marker we would expect, all right? Our OH bond is a little bit unique for a carboxylic acid. Just to kind of show our alcohol here, there was a little bit of daylight between that OH bond and our sp3 carbon and hydrogen cluster of peaks that we always see. Right? We laid down that marker at 3,000, and that big, broad alcohol peak, it all sat north of that 3,000 marker. For a carboxylic acid, it's even broader than that, and it actually swallows up that sp2 hybridized carbon, sp3 carbon-hydrogen peak. Right? So this one is my sp3 carbon-hydrogen. This big green one here that extends all the way over, this is my OH bond. All right, so that OH peak swallows that sp3 carbon-hydrogen peaks. Okay, so it's even broader than what we saw with our alcohols. It really extends at a much larger range from around 2200 to 3600, still being very strong, but being extremely broad. All right, so when you see something that's kind of eating up that normal cluster of peaks, that's characteristic of a carboxylic acid. All right, and then one more functional group that we're going to go over, specifically amines. What do I mean by an amine? So what makes amines a little bit different is, yes, an amine would have, for example, NH2. All right, but amines are really any nitrogen containing. So for example, my nitrogen just doesn't have to be bound to one carbon. It could be bound to two carbons. This is also an amine. Or all three of those nitrogen bonds can be taken up by carbon atoms. So this would also be an amine. All three of these would be examples of amines, unlike, say, alcohols and ethers, where we differentiate between whether oxygen's at the end or in the middle. For amines, we kind of lump them all into one bucket. All right? We do have a distinction here. If that nitrogen is bound to one carbon, we call that a primary amine. If it's bound to two carbons, we call that a secondary amine. And if it's bound to three carbons, we call that a tertiary amine. All right, so we do have these little subclasses within our functional group of amines. All of these would be considered amines, all right, but depending on how many carbons there are bound to our nitrogen, we would classify it as either primary, secondary, or tertiary. One of these is not terribly IR active. meaning I wouldn't see any characteristic peaks outside of the fingerprint region. Which one of these would I have a hard time seeing in my IR spectrum? The tertiary, right? Because all I have are carbon and nitrogen single bonds. Those are going to absorb in my fingerprint region. Great, going to be really hard to see buried among everything else. Our primary and our secondary, though, now we have these nitrogen-hydrogen bonds, which we can see in our IR spectrum pretty easily. They'll absorb in that something with hydrogen region. Okay? There is a little bit of a distinction that we can make from our primary and secondary amines here. So first of all, again, this would be a primary amine. This would be a secondary amine. All right, they're both absorbing north of that 3000 line, that extra line that we put down in our something with hydrogen portion of our spectrum. They're both absorbing around the exact same place, 33 to 3500. All right, they tend to be weak to medium in size. All right, the difference is that for primary amines, you actually get 2 peaks in that region, whereas for secondary amines, you just get 1 peak. So for primary amines, we get 2 broadish peaks, and our secondary amines will only see 1 broadish peak in that region. All right. The reason for that, remember, each one of these peaks corresponds to a bond being excited. Well, for those primary amines, you can excite it one of 2 ways. You can either excite it in a way where it's stretching symmetrically, so those 2 hydrogens are moving about at the same pace, and the other one, it can be excited asymmetrically. All right, we got 2 different excitations that we could have for our primary amines, which explains why we have these 2 peaks in that region. All right. Cool. So practice makes perfect here with reading our IR spectra. So now we're going to take a look at a few sample IR spectrum. And we got a few different possibilities here. I'm going to label A, B, C, D, E, F. All right. And your job, we're going to take a few minutes. You're going to try to assign each one of these spectra to one of those 6 molecules. All right, this is where it's kind of helpful to have it in front of you, but of course it's up here on the board as well. You're going to take some time, try to analyze this, try to figure out what molecule it is that we're looking at, and then we'll go through it together. there's pieces of information all over the place, right? So yes, there's definitely a peak here, but that doesn't mean that that's the only thing you must pay attention to. You want to look over here as well, all right? In your something with hydrogen region, because you do have your sp3 carbons with hydrogens, but there's also this big thing over here as well that you don't want to ignore, right? This big bit above that 3,000 mark is going to be important as well. Likewise over here, that little thing might not be important, but it might be important. It is a nice sharp peak in our double bond region. It's weak, right? But we can't just kind of ignore it outright because it's not all the way to the bottom of the graph. All right. So some peaks are inherently weak, and we still gotta look for them basically. Yeah. So it turns out for this one, you do want to pay attention to that double bond region. Yes. Yeah. Okay. Yeah. Cut it up. Take a look. Yes. Yeah, nice. That's definitely the easy one to spot. It's a good start. All right, let's do this first one. All right, so step one, I'm going to cut it up. 1,500, 2,000, 2,500, and then we got that extra marker that we lay down at 3,000. Okay? We can go ahead and just ignore our fingerprint region. Too much going on down there. We definitely don't have anything in our, actually let's just note here, this would be where our double bonds live, our triple bonds live, and our something with hydrogen. Do we have any triple bonds in this molecule? No, that we can see fairly clearly there are no triple bonds. So let's go ahead and nix that one, okay? Now, this one here in my double bond region, I do have a peak, but it is on the weaker side. And again, this is where it's a little bit more art than science. I'm not sure whether or not I should be paying attention to this, all right? It's definitely a peak, but it's pretty close to the baseline. It's nice and sharp. I don't know. We're going to just keep that with a grain of salt and note that it's there, all right? We have this cluster of peaks, although that's not a ton of information because every molecule up there has sp3 hybridized carbons and hydrogens. All right, but why did we lay down this marker at 3,000? What was the purpose of that? All right, remember, this is really what helps us. The reason that we laid this down was to distinguish between our alkenes, our alkanes, our alkenes, and our alkynes, right? If you only see peaks just south of that 3,000 marker, that's indicative of an alkane. But if we see a peak slightly above, around 3050, that's an alkene. And if it's even further up, around 33, that's an alkyne. All right, so going back to these two here, not only do I have a peak in that double bond region, I also have a little peak sitting just north of that 3,000 marker. All right, so that's indicative of an sp2 hybridized carbon-hydrogen. And my carbon-carbon double bonds, they do produce weak peaks in that double bond region. All right, so this all points to what? Our molecule A, right? Our double bond, it's got hydrogens bound to those sp2 hybridized carbons. So spectrum A is molecule A. Okay, we can note, what about our other, we have two functional groups in this molecule. What's it called when oxygen's in the middle? An ether. All right, but where do these ether bonds live on my spectrum? Our carbon-oxygen single bond, where's that going to live in my IR spectrum? in the fingerprint region, right? So ethers are not a terribly IR active. I will say carbon-oxygen single bonds, that is this peak right here. They can be some of the ones that are easier to spy. But again, if you have a really complicated molecule, there's just so much crap going on in that fingerprint region, it's hard to discern what's what. So when I'm looking at this molecule, I'm not even going to try to see that carbon-oxygen bond. I'm going to focus on that carbon-carbon double bond, right? That's what's going to be easy to spy on my IR spectrum. All right, so now let's do the next one. Again, we're going to cut it up. And then that extra one at 3,000. I can ignore my fingerprint region here. Double, triple, something with hydrogen. Do I have any double bonds in this molecule? Yes, I have this severe, very sharp, very strong peak in my double bond region, which corresponds to what kind of bond? This should be one of the more easily recognizable ones, kind of like an alcohol. If you see something giant in that double bond region, you know right away that you got what kind of bond in your molecule. That carbonyl, all right, that carbon-oxygen double bond. So we can go ahead and nix everything but these two here. All right, this nice sharp peak in my double bond region is always going to be a carbonyl group. So now I got to distinguish between D and E. The difference being is that E has that hydroxyl group as well. All right, what functional group is in E? Carboxylic acid. And remember, a carboxylic acid hydroxyl group was distinct from an alcohol hydroxyl group in just how incredibly broad that OH group absorbs, all the way from 22 to 3600, so much so that it eats up that sp3 carbon hydrogen peak. And so that's exactly what we see in this spectrum here. I can tell there is something north of that 3,000 mark. I don't want to ignore what's going on over there. And so yes, we see that same very broad, OH peak here. That's kind of eaten up my other sp3 carbon hydrogen peak. sp3. So this one here is that OH bond. All right, so this would correspond to my carboxylic acid, my molecule E. All right, let's do two more. Okay, same game here. Identify, we're going to say A through F.
also be something on top of that as well, right? Because of this.
So this is going to be important, yes, but important if you look, every single one of these has sp3 hybridized carbons. So every single one of them is going to have that cluster of peaks, right? If we go back to our previous example, you would have also seen that same cluster of peaks. You see it down here as well, right? So since they all have sp3 hybridized carbons, that's, that cluster of peaks is important. It's definitely telling you information about your molecule. But in this case, they'll all have it because every single one of them has some sp3 hybridized carbons. So it's going to be something that you can expect to appear just about everywhere.
So actually, looking at the left-hand side of that right now, tell me.
So this one is, and this is going to be a tough one here, because that's another sort of judgment call thing, right? It's kind of in the weeds there. It's not quite as pronounced as something like that. But based on that carbonyl peak, what would you say that it is, just looking at this selection? Carbonyl being carbon oxygen double bond. So that's one of them. And so you want to think about what you would need to see or not see that would help you distinguish between those two.
Because you said anything with hydrogen or OH would be more further to the left side. I mean, sorry,
It would, all right? But there's another characteristic of that OH that's really important that's absent from this spectrum, and that is that the OH bonds are always absorbing very strongly, right? So this little weak signal down here would correspond to an OH bond. It's not broad enough, it's not strong enough, right? So this here, so this would be for carboxylic acid. If you want to go to the last example. So this is A, B, you were just at C, go one more.
Oh, sorry, I only took.
Oh, okay, gotcha. There's this one here. This is another OH peak right here. But again, nice and strong, right? So something that's down here wouldn't be an OH bond. It's always something that's really, really strong for OHs. But again, all right, so first of all, speed record here. F. What does that one correspond to functional group-wise? That OH bond. So that sharp, or rather strong, broad peak over here is going to be one of the easier ones to spy that will correspond to our alcohols. All right, so this peak right here just kind of jumps out as an alcohol peak. We, of course, also have our sp3 hybridized carbons and hydrogens, right? But that's not the most information because just about all of these molecules here have some sp3 hybridized carbons with hydrogens, right? So not that it's not important, but we would expect to see that in just about every one of our spectra. It's that OH peak that jumps out, letting me know it's an alcohol. Okay, so then for this one here, we're going to have to cut it up. We're going to have to do it the long way. 1,500, 2,000, 2,500, and then that extra one. All right. We see here the dead giveaway is that we have this nice, strong peak here. Not strong, maybe medium. But that's sitting in our triple bond portion of our spectrum, right? So right off the bat, I can conclude that this is which one of our examples? It's going to be C here. There's another peak here that allows me to conclusively determine that it's C, because if we notice that C, that triple bond's on the very end of that molecule, meaning it's got a hydrogen attached, and that's again what that extra marker at 3,000 helps us see. If we have something that's sitting well above that marker, around 3,300, that is my sp hybridized carbon and hydrogen bond absorbing there. Right? So we see that carbon-carbon triple bond absorbing in the triple bond region, but we also see that carbon-hydrogen bond, my sp hybridized carbon-hydrogen, absorbing in that something with hydrogen portion of the spectrum. And then I have that same cluster of peaks I always see, corresponding to my sp3 hybridized carbons and hydrogens. All right, so we're going to pick up with this next time. We're going to kind of piggyback. We're going to learn a new experimental technique, but we're always going to kind of use information from these other ones as well to help us deduce what our molecule is. All right, so we'll get a lot of practice with these IRs as we go.